All right. So, first thing that I want to talk about, the first topic I want to hit on is temperature. So, we need to get an understanding of what temperature is. Temperature is not how hot or how cold it is in the room. Temperature is has a lot to do with. Don't write what I have up there just yet. I'm going to give you a definition of temperature in just a minute. Temperature has to do with energy of atoms inside of something. So temperature temperature is the measure of the average kinetic energy in matter. So our body temperature is based off of how the atoms in our body are moving, or how much those atoms are moving. And so everything has energy, even something that's stationary like a rock. Those atoms are moving to some degree. And if it's exposed to like something like solar energy, it's going to cause those atoms to move a little bit more. That's why they have expansion joints in roadways, because that concrete expands and contracts. That's why that's why they put the little rubber seals on like your car doors and all of that, so that when it gets hotter inside and all of that, that the pressure doesn't cause your windows to blow out, things like that. All right, but that's what we need to understand with temperature. Now, in the United States, what is the primary temperature scale that we use? Fahrenheit. All right. What, according to the rest of the world, what's wrong with Fahrenheit? All right. So let me ask this question: what's the freezing point in Fahrenheit? All right, freezing point of water. Thank you for correcting me on that. That's not the freezing point of everything. Water freezes at 32 degrees Fahrenheit. What's the freezing point, or what's the boiling point of water in Fahrenheit? Does anybody say it again? 212. Good job. All right, 212. All right. Now, is there any pattern in those numbers that we can really recognize? All right. So let's go to, what does the rest of the world use? Celsius. All right. What is the boiling point, or not boiling point, what's the freezing point of water in Celsius? 0. What is the boiling point of water in Celsius? 100. All right. Does that one make more sense? Base 10. So this is a better scale. All right. It's a better scale because it allows us to do easier math. All right. Base 10 math is a lot easier than whatever that is. When I took calculus in my first year of college, I knew, because I liked chemistry and all of that, I knew the formulas to convert Celsius to Fahrenheit. So this question was like the hardest question for me to answer. They wanted me to derive the formula for that. So like I had to work backwards. But I'm like, I know the answer already. I can't explain how it got there. So that, it was like devise an equation to solve for all that. And so everybody around me looks at me and I'm like, well, this is the equation. I know what it is. And because for every 5 degrees you go up Fahrenheit, you go up 9 degrees Celsius, or put that, every 9 degrees Celsius you go up 5 degrees Celsius. And if you line the scales up next to each other, you can make an arrangement and all of that. And that's what he was wanting us to do. But I was like, I already know the answer. I don't need to do all that. All right. So here's the thing. I don't really care that you know who did it. I'm putting it up there because some people like this kind of stuff. 1742, Anders Celsius used a mercury thermometer. He defined those points. In Chem 2, towards the end of the year, I may do this. I have some thermometers that are absolutely blank, all right, and Sharpies. And we can actually set on that thermometer, we can define freezing point, and we can define melting point of water. We can define boiling point and all of that, and we can actually fill in the units in there, and we can create either a Celsius scale or a Fahrenheit scale, depending on how we want to do it. All right, but that's what he did. He had this glass tube that had a mercury reservoir on it. He stuck it in water, and he stuck it in frozen water, and he marked that as his 0. And then he went and he boiled. He brought that ice, melted it, and brought it to boiling point, and he marked that as 100. And then he broke it down by tens in between. Fahrenheit was done a similar way. They just for whatever reason, they picked 32 as the freezing point. All right, now, advantages of Celsius scale. We already talked about this. It's a base 10. It's on a scale of 10. All right. Disadvantage is this. What if we're not measuring the freezing point of water? What if we're measuring the freezing point of nitrogen or carbon dioxide? Has anybody ever dealt with dry ice? Like for food packaging and all of that. All right. Dry ice, you might have seen it at a Halloween party or in a theatrical presentation. What do we use dry ice for? Or what did it smokes? All right. So it goes directly from a solid to a gas. It doesn't have a liquid phase, or it has a very small liquid phase. So this freezes at a much lower temperature than water. So if water is 0, and this freezes at, I'm just pulling this is not the right number, but let's just say that it freezes at 100 degrees lower than water, what's going to be the problem with the number that we get? Negative. So the disadvantage of this is it has negative numbers. So there's an arbitrary 0 value. It's not a universal 0 value. All right. So if you don't want to write that, you can say and really the only problem with negative numbers is we forget to count 0 whenever we're going across that scale. So we miscount it. We usually are off by 1. And then when we're multiplying and dividing things and it's built into an equation, having that 0 in there throws off our calculations from time to time, because what happens when you multiply or divide by 0? Or multiply by 0, you get 0. If you divide by it, you get, what is it, unknown or error or whatever. All right, you can't do it. So that's the issue there. So anyway, he did the work for us. This is the formula. Now, I'm going to give you a formula I like better because I don't like fractions. All right. If you flip into the reference packet that I gave you, flip to the second page of that and look in the bottom left-hand corner. There's going to be a list of formulas and conversion factors and all of that. That's going to give you a formula for solving for Celsius from Fahrenheit. All right. That formula should be degrees Fahrenheit minus 32 divided by 1.8. All right. So if I want to solve, if I'm given a number in Fahrenheit and I want to solve for Celsius, I can use this equation. Either one of these say the same thing, because 5/9, if we're multiplying by it, it's just the inverse of 1.8. All right. So So degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8, or degrees Celsius equals 5/9 times Fahrenheit minus 32. It's the same equation. Yes.
Is to convert both? Like,
So if we had Celsius, I'm not going to make you do it, but you should be algebraically to. If I had Celsius and I didn't have that, we can manipulate the equation to get there.
I'm saying, like, does it work both ways around? Like, can you use the same equation to find out both?
Yeah, you would just leave that as your x, but I'm going to give you the other one. So Fahrenheit, solving for Fahrenheit, it's using the same numbers. Manipulating the equation to solve for Fahrenheit directly is going to be 1.8 times degrees Celsius plus 32. So we would just manipulate to get there. All right. Both of those formulas are already on this sheet. All right. So I'm trying to show you this sheet is going to be kind of like your lifesaver. You'll have access to a sheet just like this every test we take. All right. Basically, every answer is on here in one form or another. You just have to know how to use this. All right. I am all about using the resources that are made available to you and learning how to use them. All right. So with that said, what is normal body temperature, or what is the average normal body temperature? 98.6. Without using Google or anything like that, tell me what that would be in Celsius. So try to solve that for Celsius. And actually let me go the full number, 98.6. 98.6 degrees Fahrenheit equals. All right, if you have it, let me just come around and see if you have it, and then we'll.
It's like a messy dusty. Oh.
Yeah, he was trying to throw you off. All right. Yes. Yes. All right. So you probably got 37. I would have probably written this as 37.0 because all of this is a given set here. I'm going to use my initial values as my rule for sig figs. All right, so I'm going to use my given there that I had 3 sig figs in it, so I'm going to put my answer in 3 sig figs. So that 0 is meaningful in a way just to let me know that I measured it to a 3 sig fig initial precision. All right, now I could give you another number and ask you to go backwards. I'm going to do that a little bit later. All right, so this is homework. It is not due in class today. Oh, wait, let me go through one more thing before I say that. I'm going to give that out in just a minute. All right, so there is one more temperature scale that we have to deal with. Kelvin. So, chemists and physicists do not like negative numbers. So they had to approach a way to get around those negative numbers. So, and I forget his name, but 1848, Lord Kelvin developed a scale that relies on the average kinetic energy of atoms. But basically, he changed the Celsius scale. Kelvin and Celsius are the same scale. They're just offset by a factor. All right. So he wanted 0 to be a universal constant, not just based on water. All right. So what he did is he set the idea of absolute 0. Does anybody know what absolute 0 is? That is the theoretical coldest possible temperature. all right, we can approach absolute zero. Liquid nitrogen's getting pretty close, but we can't get there, all right? There's, if you take physics and all of that, you can look at the debates on it and all that. What would happen if it happened? You can go down that wormhole on YouTube if you want to on your own time. I just know that absolute zero is the theoretical temp theoretical temperature where atoms stop moving. All right, that's all motion stops. All right, so what are the advantages of having a temperature scale like that? All right, it is empirical, means it doesn't change. All right, it's universal, it works all over. There's no negative numbers, and it's still a scale, it's still a base 10 scale. All right, they're really, as far as chemistry and physics is concerned, there are no disadvantages to Kelvin. All right, Kelvin always works. All right, now, so to convert Kelvin, we can only convert directly from Celsius to Kelvin. Kelvin is offset by a factor of 273. And if you look on your reference packet, I actually have that Kelvin is degrees Celsius plus 273.15. All right. It really just depends on how precise we're trying to be with our answer. All right. Yes. The same reason if you go to your, and I'm just throwing, if you go to your set in his ways uncle and ask him why the United States uses miles per hour versus kilometers per hour. All right. People are kind of set in their ways. You know, if you go to an older mechanic and he's looking at a bolt, he's going to give you the English fraction version of it, and another mechanic's going to look at it and give you the metric. All right, they're close, but they're not exact. So I guess the main reason why we don't use Kelvin is because people would get worried about if you ask me what the temperature of this room is, and I told you it was 297 Kelvin in here, people would freak out about that number. All right. That's probably the real reason. It just makes numbers that are a little bit bigger that throw people off. All right. No, we can approach it. We don't reach it. There's a lot of theories of what would happen. There's a lot of end of the world theories of what would happen. I'm not going to go there. I don't know black holes. I don't know physics that well. I was decent enough to get A's and B's in my courses that I had to take. I'm not good enough to teach anybody it. All right. So that kind of wraps up what we're doing with this for now. All right. Let me freeze this just for a second and pause my video.